Hello everyone, and thanks for watching Edupedia World Videos. In this video we'll discuss power as well as see some examples in which these concepts can be used. Let's take a brief recap of what we've done till now. We saw many formulas and I'll try to summarize them here. For a single particle, the work done, which is obviously the work done by external forces, since a single particle does not have any internal forces, equals K2 minus K1, which is the change in kinetic energy. This is called the work energy theorem. For many particles, that is, for a system of particles, we have two formulas. One is W external plus W internal equals K2 minus K1. But what is W internal? W internal is equal to negative of U2 minus U1, right? That is the definition of potential energy. Change in potential energy is the negative of the work done by internal forces. Correction, by internal conservative forces, right? So another way this can be written as is W external. Now when we derive this, we assume W external to be 0, but if there is W external, the generalization is easy enough. This comes out to be K2 plus U2 minus K1 plus U1. This is the total mechanical energy final, and this is the total mechanical energy internal. Remember, mechanical energy is just the sum of the kinetic and potential energy of any system, right? So if there is no work done by external forces, right, and there are only internal conservative forces, then the mechanical energy of a system remains constant. We can interchange between kinetic energy and potential energy, but the mechanical energy will remain constant. If there is external forces doing external work, then the total work done on a system of particles equals the change in mechanical energy. That is the change in kinetic energy plus potential energy, right? So the final thing which we need to see is power, right? So the differential amount of work done is defined as F dot dr, and power is nothing but the rate of work done, that is how fast the work is done. So it is defined as dw by dt. Just like velocity is rate of change of position, power is rate of work done, right? So that can be seen to be F dot dr by dt, that is F dot v. So the dot product of the force and the velocity give the power, right? The unit of work done, the SI unit is joules, and the unit of power is watts, right? So now we've discussed all the concepts we need to know. So let's see some examples. Okay, so let's start with a relatively simple problem. Yeah, so just assume this is like a hill or something, dip in a hill, right? Let's say this height is 10 meters, and let's say this height is 4 meters. This surface is smooth meaning frictionless, so friction will not be acting. We just gently push an object with almost zero velocity from this point, and it obviously moves down, right? So it moves down, and once it reaches this point, it has a speed v. We want to find out what the speed v is. So if I leave an object here, what is the speed by the time it reaches this point? I'll try to do it in two ways. The first way, I'll use the work energy theorem, right? So in that case, I will take this object to be my system. If this object is my system, then what I'll say is the work done is equal to K2 minus K1, right? Remember, this is the work done. Now I need it's Actually, it's much more easier, I find, to learn concepts through problems. So please pay attention to the specifics I'm saying, because they'll be important. The first specific, what system I'm choosing. When I'm applying the work energy theorem, my system is this single particle, nothing else. So the work will be the work done on this particle by all the forces. What are the forces acting on this particle? There is mg acting downwards, there is a normal force acting, and that's it. There is no frictional force acting, right? We know that the normal force does not do any work because it is always perpendicular to the surfaces in contact, and the velocity is in the direction of the surface. So the force is always perpendicular to the velocity. Gravity is the only force that will do work. We know how much work gravity does, that is mg times h2 minus h1. Right, that's what we derived earlier. For constant forces, we can just take the dot product of the force and the displacement. The displacement would be this. The force is in this direction. I forgot to give the mass. Let's say the mass is 2 kgs. Right, though we find out that we don't really need the mass to find the velocity, but let's take it. So this mg acting downwards is 20 newtons, and this is the displacement. For the dot product, this into cos theta. Right, this length times cos theta becomes this height. Right, if we take this triangle, and this height is 6 meters, 10 minus 4. So the work done by gravity is 20 newtons times 6 meters, that is 120. That is equal to K2 minus K1. K1 initially was 0, right? Because I just nudged it, I didn't give it any speed. So it's simply equal to K2. K2 will be equal to half into 2 into V final, or just let's say V squared. That means V is root of 120. I apologize for any random not integer type numbers which might come up, because I'm just making these values off the top of my head, right? The important thing is the concept. So we found out that the speed was root of 120. Now I'll try to do it in a completely different method. We didn't use potential energy now, right? We took this single particle as a system and we applied the work energy theorem for a single particle. Now what I'm going to do is I'm not going to just take this particle as a system. I'm going to take this particle plus this hill plus the combined earth as a system. I'm going to take the earth with everything in it as a system. In that case, gravity is no more an external force. Now it becomes an internal force, right? Because it is a force acting between two components of the system, the earth and this particle. The work done by normal force will still be 0, and still there is no friction acting. So in this case, the work done by external forces on this combined system is 0. Right, now again the terminology is very important. The work done on this single particle is not 0. It is 120 joules. But the work done on the combined system by external forces is 0. So in that case, the total mechanical energy will remain conserved. So I can say U1 plus K1 will be equal to U2 plus K2. Right, we know that K1 is equal to 0, so I'm just going to remove it right now. Right, we know that K1 is equal to 0. Now another thing which is important, which we'll see here, is the concept that we can choose 0 to be any point. So let's say I take this level ground to be U equal to 0. That is the most convenient choice in most cases. We'll take the ground to have gravitational potential energy 0. So what is U1? U1 is the potential energy at this point. That is mgh. That is 20 multiplied by 10. So this is the initial mechanical energy, 200 joules, right? Now, what is the potential energy at this point? That is mg into 4, so 20 into 4 plus K2. K2 will be half into 2 into V square. This gives me 200 minus 80, 120 is equal to half into 2 into V square. So again it gives me V equals root 120. So we see that we got the same answer. Now, let's try to do it in the third way. Let's try to do it just like this, but instead of taking this as U equal to 0, I take this as U equal to 0. Right? So in that case, U1 is now mgh, but h is measured from this reference point. So this is 6. So now I have 20 into 6 is equal to, now U2 is 0. The final is 0, right? I am at U equal to 0. So U will be 0. So this is equal to half into 2 into V square. So this also gives me V equals root 120. If just for fun you want to try it, you can take this position to be u equal to 0, or you can take a position which is 1 kilometer above the ground to be 0. No matter what you take, we see that this is basically, I'll just try to do it in variables. This will be mgh1 and this will be mgh2. So to find the kinetic energy, all that is needed is mg into h1 minus h2, right? So what h1 and h2 individually are does not matter when we are trying to find this thing, the speed. Note that the mechanical energy does depend on the choice of reference, right? So if we take this to be u equal to 0, then the mechanical energy at this point is 200. But if we take this to be u equal to 0, the mechanical energy is 120. So mechanical energy incorporates potential energy as well, so it is dependent on the choice of origin. Kinetic energy is not dependent on the choice of position, and the quantities generally of interest, such as speed or maybe compression in a spring or displacement, these are independent of choice of reference, right? So I hope this example has made things clear. Let's try to increase one more aspect of this example. So let's say I have an inclined plane like this. I just drop an object from here, just nudge it, again smooth, completely smooth, and this height is, let's say, 10 meters and mass is, let's say, 2 kg. So the easy question could be what is its speed when it reaches this point, the ground? And that's easy enough. mgh is again, I could do it in both ways. I'm just going to do it in one way now, and I'm sure you've understood that all ways are equivalent. So work done will be 2 into 10 into 10, that is 200. 200 will be half into 2 into v square, so v will be root of 200. But instead of asking for v, I could ask for something completely different, right? And this is something which, though you may not generally see in your school level papers, when you go into entrance examinations and you're trying to solve harder questions, this is one of the key ways in which they try to make questions hard. They'll take two separate concepts from within a chapter and use them in the same problem, or they might take two separate concepts from two completely different chapters or completely different units and add a question. So in this case, I'm going to add another thing. This was gravitational potential energy, and now I'm going to attach a spring at this point to make it slightly harder. And let's say I give the spring constant equal to 10, right? I apologize, the block shouldn't be here right now. It's not here yet. So we know what's going to happen. This is going to come down with some speed. With what speed we just calculated, root 200. It is going to touch this spring. It is going to start compressing this spring. The spring is going to be compressed to some extent. Then the spring is going to start extending and it will go back up. And if there is no friction at all, it will just move to and fro between these points. What I am asked is, what is the maximum compression of the spring, right? So this is the spring now. When the block reaches the spring will be something like this, and it will be compressed by a certain amount. What is that amount? So again, initial mechanical energy is 200, right? Because that is the potential energy due to gravity. The kinetic energy is 0, and the potential energy of the spring is 0 because it's initially at its natural length, right? So initially mechanical energy is 200. Finally mechanical energy also has to be 200. The gravitational potential energy is 0, right, when it reaches this point. What have I taken gravitational reference to be? I've taken it to be this. This I've taken to be u equal to 0. By the way, for gravity, we generally have a choice which we want. But for spring, in 99% of the cases, it will be most convenient to take the natural length to have u equal to 0. We could take the natural length to have u equal to 10. And then the potential energy of the spring will, instead of being half kx square, will be 10 plus half kx square everywhere else, right? And it will all ultimately cancel. So 200 is equal to, now when the block has touched the spring, it has two types of energies. The kinetic energy of the block and the potential energy of the spring. I am taking the block plus the spring to be my system, right? But when it is at a maximum compression, the speed will be 0, right? Because the block touches the spring, then it's moving a little bit towards the right and the spring compresses. It moves more towards the right, spring compresses. When the spring is not compressed anymore, that means the block is not moving towards the right anymore. That means the speed of the block is 0. So at maximum compression, the kinetic energy will be 0. So all of this potential energy due to gravity was converted intermediately to kinetic energy, and now all that kinetic energy has been converted into potential energy of the spring, which is half kx square. So half into 10 into x square, which gives me x equals root 40. Right, so this way we were able to find the final compression of the spring as well. Right, now one more important problem which also incorporates a previous chapter of circular motion is something which sometimes gives a little bit of confusion to students, and that is motion in a vertical circle. So up till now we've seen pendulums which use ropes, but for the cases of simplicity and understanding, I'm going to use a rod for now, not a rope. Later I'll use a rope as well, right? So we know the differences between ropes and rods, we've seen them. Ropes can pull, but rods can pull and push both, right? Ropes do not have the ability to push. I cannot push an object by pushing a rope attached to the object. I can do it with a rod though. So for now, there is an object, there's a bob. This length is r, let's say. The mass of the bob is L. Attached to the rope. Right, attached to the rod, sorry. And I give it a speed v. Right. So it will move in a, if the speed v is relatively small, it will move like this, to and fro between these 2 points. But if I give a large enough speed, it might even complete the whole circle, right? So let's say I give the speed v equal to root 3 gr. These values are slightly important and I'll deal with them later. Right now, just assume I've given the speed v equal to root 3 gr. It will go up, it will go up, it will go up to some point, and then it will stop. I don't know why I drew it like this. And then let's say at this point it stops. V becomes 0. And this angle is theta. We have to find out when the speed becomes 0, right? So the question is simple enough. Depending on a particular speed which we give, it might just move like a simple pendulum between these 2 points, between these 2 quarters. It might move up to this quarter, which if this is a coordinate axis, this would be the first quadrant, and stop there and then come back and move like this, or it might complete a vertical circle, depending on the range of speeds. Let's calculate what happens with this speed. So we'll use conservation of energy. The tension will never do any work, right? The tension either by a rope or the rod will be perpendicular to the velocity at every instant. So the tension does not do any work. The only force that does work is gravity, right? And how much work has the force of gravity done? This is r, this is r. So this height is r cos theta. So this total height is r plus r cos theta. So work done by gravity is mgr times 1 plus cos theta. Right. This should be equal to the change in kinetic energy. The final kinetic energy is 0. The initial kinetic energy is 3gr. Is half into m into root 3gr whole square. Right. So this means mgr times 1 plus cos theta equals 3 by 2 mgr. So mgr plus mgr cos theta is 3 by 2 mgr. That implies cos theta is equal to 1 by 2. From that we can calculate the value of theta. Now we see why I took this particular value, because I know for this value it will end up in the first quadrant. Okay, what value would it have to be for it to end up here? This v equal to 0. In that case, this would not be mg into r into 1 plus cos theta. It would just be mgr, right? And this would be v. So we would get mgr is equal to half mv squared, which gives me v is equal to root 2gr. So for a speed smaller than root 2gr, it will move between these 2 quadrants. For a speed equal to root 2gr, it will reach this point, right? For a speed greater than root 2gr, it will move up and it might even complete the circle. The next question we want to ask ourselves is, what is the minimum speed which we need to give so that it completes a vertical circle, right? So let's try to do that. In that case, it will be at this point. Right. Now, if we give a very high speed, it will complete a vertical circle, and at the top it will have some speed as well. Right. Let's call it V1. If we give a slightly lower speed, it will complete the circle, but the speed at the top will be lower. For the minimum speed we need to give, so that it completes a vertical circle, the speed at the top should be 0. Right. So if the speed at the top is 0, the work done is mg into 2r. Right. So W gravity will be 2 mgr. The final kinetic energy we take to be 0 because we want to find the minimum speed, and we need to find this. So this is equal to half mv square, which gives me v equals root of 4gr. So the minimum speed we need to give it a bob so that it completes a vertical circle is equal to root 4gr. Right. That's easy enough. Now let's try to analyze what happens in this case when we give a speed equal to root 4gr. So this was the bob initially. Finally it's like this at the top. Now at this point it has been moving in a vertical circle. It has been doing circular motion, and the speed at this point is 0. Right? So let's draw a free body diagram of this object. There's mg acting downwards, and there's a tension acting. And what is the acceleration? The acceleration is 0. Right? There is no tangential acceleration because there is no force in the horizontal direction. There is a radial acceleration in circular motion which is equal to v squared by r. But at this topmost point, v is 0. So the acceleration is 0. So that gives me, by Newton's second law, mg plus t equals 0, which gives me t equal to minus mg. Interesting result. That tells me that the force acting on this bob due to this rod is mg in the upwards direction to make the net force 0. Now things get a little bit tricky. Right? We can understand this in terms of a rod, that at the topmost point the speed is 0. That means at the topmost point the bob is momentarily at rest. So if mg is acting downwards, the rod must be pushing the bob upwards with a force equal to the gravitational force such that it remains at rest. Now it will become interesting because now I'm going to see what happens if I use a rope instead of a rod. For a rod to push this bob up with the force of mg is completely reasonable, but we know that a rope cannot do that. Right? So if I want to find out what is the minimum speed v I must give so that it completes a vertical circle, where this thing which attaches the bob to the ceiling is not a rod but it's a rope, then a completely different scenario arises. In that case, we cannot have v is equal to 0 at the topmost point. Right? V is equal to 0 at the topmost point demands that t be mg upwards. For a rope, t cannot be mg upwards. T cannot be upwards or away from the center ever. Right? So in case of a rope, what do we need to do so that it moves in a vertical circle? We want to make the t equal to 0 at this topmost point, because v is equal to 0 is out of the question. So we will have some v. Right? And the higher the tension we have downwards, the more the acceleration will be, the more v will be. Right? The smaller the tension is, the smaller v will be. What is the minimum possible value of tension for a rope? It's 0. It cannot be negative. For a rod, tension can be negative, meaning it's pushing. For a rope, it cannot be. What will be the value of the speed if t is 0? So then we need to find out the acceleration. Right? And t is 0. If t is 0, these don't apply, and we get mg is equal to mv squared by r, which gives me v equals root rg. So at this point the speed is not 0, it is root rg. Right? Again, work done by tension is 0. We'll try to solve the problem as before. Work done by gravity is 2 mgr. This will be final kinetic energy minus initial kinetic energy. Right? And that will be, actually the work done by gravity is minus 2 mgr. Right? Final kinetic energy is half into m into gr. Right? Because root rg whole square. Minus initial kinetic energy is half into m into v squared. Right? So from that we can see that half mv squared is equal to 5 by 2 mgr, or V is root 5 gr. This is the interesting result. Everything else is the same for the rope and the rod, except it's much easier to put a rod into vertical circular motion. And I hope this makes sense to you intuitively as well. A rod can be at rest at the topmost point, but still not collapse. If in a string the speed is 0 at the topmost point, the string will just slack and the object will start moving downwards, right? The string will not remain extended. So for a rod, we need to give a minimum speed of root 4 gr so that it can move in a vertical circle. But for a rope, we need to give a minimum speed of root 5 gr. Other than that, the analysis is pretty much the same. If we have to find out the speed at any particular point, we just find the work done due to gravity and we just equate it to the change in kinetic energy. This completes work, energy and power for us. I hope this topic has been you've understood it pretty well, because this topic is very important in future courses. When we do gravitation or when we do thermodynamics, we will repeatedly use conservation of energy, and the only thing we'll be doing is we'll be adding different types of energy. For example, we will see a new formula for gravitational potential energy when we take the gravitational force to be the general formula G m1m2 by r square. We will see a formula for electric potential energy, right? So these things, different forms of energy will be added, but the concepts will remain the same. The work done for a particle equals change in kinetic energy. For a system of particles, the work done by external forces is change in mechanical energy, and the work done by external plus internal forces is change in kinetic energy. Thank you.